Hello everyone, and welcome to the first episode of the Game Dev McGill tutorial series. If you're not familiar with Game Dev McGill, we are a student-run organization at McGill University with a goal of promoting game development to the greater student body of McGill. So in this tutorial series, we're going to be going through a workshop to try and build a simple game. Our goal is to cover some important elements required to build some basic 3D games, to get you started with Unity, to provide assistance as we go through this together, and to share some of our knowledge, some of the members who are more experienced knowledge. So in terms of prerequisites, if you're watching this and if you're McGill, we do expect a base level of coding knowledge. Now we'll be explaining any more complicated stuff that we use, but at least a Comp 2 level of programming knowledge. So you can code a tiny bit. You know what a variable is. You know how to put things together. You can maybe debug a bit. We do also expect a bit of like a basic understanding of linear algebra. So you should know what a vector is. You should understand how to add vectors together, how to do a dot product between vectors, what a cross product is. Often when if we use any of these operations, we'll explain why we're using them, if we do. But it's still good to be familiar with it because it'll help you visualize stuff. You should be able to run the Unity 3D game engine because that's what we'll be using. So being familiar with that, at least getting around with it will make it easier for you. And, some enthusiasm to learn. So, as you can see, this tutorial will be recorded and uploaded on YouTube as often as we can. We will be making the source code available on GitHub. During the live sessions, we'll be taking questions, so there will be live sessions of these tutorials happening about once per week. And if you have any questions, then if you're a member of Game Dev McGill, you can feel free to ask questions on our Discord or show up to our club room. So, without further ado, let's get into it. So we're going to be building a third-person game where you can walk through an environment, pick up some resources, and build and destroy some blocks. Excuse me. The game will be sort of similar to Minecraft, but with pretty much a lot less stuff. The screenshot on the left is sort of midway through the tutorial what it's going to look like. By then you'd have a character moving around who can pick up blocks and like select a place to drop blocks. And throughout this we're going to be going through some very simple things to show you, like how to build components which you might always want to build, like a character controller or anything else. So for this session, our goal is to build a movement controller, a camera controller, some sort of unified input handling, and if we have some time, to add a character model and maybe even the character animation. And as I said, all of this, the finalized repo and project, will be available on GitHub for every single tutorial session. We will be alternating for tutorial sessions between myself and someone else, but the code will always be available. So yeah, so now let's get into the guts of this. So we're going to be using Unity 3D. There's a lot of information which you don't need to go through all at once right now, but all you need to know is that Unity 3D is a game engine. You've most probably already used it if you've gotten into the club, if you just do your rollerball tutorial. And if you haven't been to our Introduction to Game Development and Game Engines talk, just, like a game engine is basically just a collection of tools which you can use to build your game. So what Unity is going to do is it's going to take care of a lot of like the brunt work of rendering, the physics, and a lot of event handling, which will allow you to get like input and stuff, and give you sort of a place for you to insert yourself into this engine and modify a lot of those behaviors without having to rewrite a lot of this like kind of boilerplate, a lot of this more complicated stuff. So you don't have to rewrite your own physics, but you could modify the physics or write your own physics if you do want it. If you just want basic physics, you can have that. And we are going to be specifically using the scripting behavior, which allows us to add some game behavior to the game, and all of these will be running in the game loop, which you should be familiar with more or less till now, which is, just a loop that runs once every frame and calls a set amount of functions. Again, if you're not familiar with this, I might recommend going to look up a bit our Intro to Game Development talk, Intro to Game Engines talk, given by Michael. But you can also look it up online. Looking up Unity Game Engine Entity Component System will kind of give you a good idea, or like Unity 3D Game Loop will yield you this picture on the right, which kind of gives you an idea of how the flow of the engine runs when you're running a game. So this here is Unity 3D, so I'm assuming all of you have gotten it. Right now, all I did was I created a new scene, a new project actually, which I just called Tutorial 1 GDM. There is nothing. This is the default settings in the project, and I just went to the scene and I opened a sample scene. So yeah, so for right now, that's all you need. You just need the sample scene. So went through this, we created a new Unity project. Next thing we want to do is we want to get some movement. We want to get something happening in the game. So let's jump right back into Unity. First thing we're going to do is we're going to go into our sample scene, which we can keep as a sample scene for now. I'm going to add a 3D object, and let's add, I don't know, let's say a capsule. There we go. Now we have a capsule. And as you can see here in the game window, you can see it rendering. I just centered it back. You can see it rendered. It's all good. If I click play, not much is going to happen because there's nothing happening. If I move it in the scene, you can see it that it is moving. You'll have to forgive any lag due to the recording, but you should be able to get an idea that, nothing's happening unless I move it in the scene. So we want it to be able to move like a character when we get some input. So before we start doing that, maybe let's define a bit more kind of what we want out of this behavior. So we want to get some input. We want to update the position of the character, and we also want to update the rotation, so it's like facing the right way. So first things first, let's kind of think about the input. We can think about so the way we're going to do it, and there's many ways to do it, but the way we want to do this is that we want our input to be on the WASD, or the arrow keys, and we wanted that, like, if you take this little circle here as our character, and you have these arrows kind of representing its like local coordinate axis, or if you want the way it's facing, sort of. If you look at here, the W, let's say this is the front of it. It's hard to tell, there's no face on this. Let's assume this vector here is the face, is the front face of the thing. So you see here it's facing up, here it's facing at like 45 degrees roughly, and here it's facing down. We wanted that no matter when it's facing this way, when we click W, it goes in that direction. When we click D, it goes 90 degrees clockwise from that front-facing direction, right? So we want this movement to be kind of relative to the character's orientation, right? So that's one thing you want to keep in mind. We jumped a bit too soon. So let's go back into Unity. Let's create a folder for our scripts, because we're going to want a script. So let's create a script folder. And in the scripts folder, we're going to create a C# script that we're going to call movement controller. And then we're going to double click this movement controller to open it up in Visual Studio, which is going to prepare our solution, open it up, hopefully. Let's see, you probably will not have that issue. because I already had it open something else. All right, there you go. If you can't find it, just you have to drop down here. Just go to your project, just assets, script, movement controller. Awesome. So, like we said, what do we want to do? We want to move the character in a specific direction. So let's have a method, a public method that will be able to be called move, and we want to take vector2 movement, and that's going to be our input. So call it movement, or you can call it input. I call it movement, whichever makes more sense to you. You can feel free to tell me whether you think that I have terrible variable naming convention, but feel free to use what is clearest to you, and add some comments if it's not clear. We're also going to take a vector3, which is going to define our forward vector. So if I go back to the slide, we want to take a vector that tells us, okay, where is this W facing? Like, is it this way? Is it this way? Is it this way? Right? Like in which way are we going? And so this might seem a bit odd right now, because you might be like, oh, well, like you should have this information yourself, right? Because it's the way you want to walk in the direction you're rotating, your character is facing. So that's why I'm going to make a small correction. So that's one way we could do it. Doing adding these parameters in this method allows us to basically decide, all right, when we click W, we can go into an arbitrary coordinate axis. So if this just happens to be the way they're rotated, right? If the character is rotated this way, they move this way. Perfect, dandy. And then we just pass in the character's rotation. But what if we, for example, don't want to match the character's rotation? In our case, sorry, I made the mistake earlier. We want to match the camera's rotation. We kind of want to walk in the direction of the camera. If you think of some third-person games, when you rotate the camera and then press forward on the stick, you go forward in that direction, which is kind of the direction that we kind of want to face. Regardless, having this method kind of look like this allows you to decide afterwards which one you want to do, and that's it's a good practice when you writing code to kind of try and make it generally as extendable and reusable as possible. So what do we want to do? So basically, we'd like to move. So let's say we have some vector3 velocity, right? And we want to move in that direction. So what we're going to do is we're going to take the forward, and then we're going to multiply it by movement.y. So movement.y is going to be how much we want to move up, right? So this is just a map, an arbitrary mapping that we decided to do. And then we're going to do right times movement.x. Okay? And then just this alone here, this is going to return us a velocity vector, which is oriented in the direction and in the axis that we defined, right? And it's going to be like, okay, well, move forward in this axis by some amount that we pass in, and move right by this amount. So it'll allow us to move diagonally and not. And if you pass in negatives, so you might be wondering, why did we only pass in 2 vectors and not 4? Because we have 4 here. Well, if you pass in a negative for the forward amount, for the y, well, this s is just the flip of w, right? So you can achieve the same thing by just passing a negative. You don't need 4 different vectors. All right, and so let's let us continue. All right, sorry about that. Was having a bit of trouble with my computer. So picking up where we left off. So this will define sort of our velocity vector, and we want to actually apply this to something. So like I said, Unity is a game engine which comes with a bunch of cool things like a physics component, like built-in physics calculations. One of those is the rigid body, which is a component that applies physics to the object it's attached to. So we're gonna take in a rigid body here, and we're gonna say that whatever this is connected to must have a rigid body. So adding in m underscore rb, which is like a member rigid body, so we can use this variable. We're also going to add in as a tag here, we're going to add require component type of rigid body. And this just says that in Unity, when you add this component, this here movement controller, it needs a rigid body. But it also means that if you try and remove a rigid body and this component is connected, you can't remove the rigid body. So as long as this component is on an object, it will have a rigid body, which will allow us to do something like this. Now, keep in mind, so this here is trying to ensure that when we do this, we know that we're getting something. Now, yes, there are ways where when this ends up being called, something else remove the rigid body from it, but roughly speaking, we can assume that it is still there. So now that we have the RB, we're going to come in and do if movement not equals to vector 2.0, we're going to do this dot transform dot forward oh, sorry. Well, this is for something else, which I have accidentally started adding a bit hand. We're going to do m underscore rb dot velocity. So you'll excuse me, this is one of the first times I do a tutorial, so trying to keep track a bit of my notes, but I'll get back to this line of code right here. The thing we actually really want to do is we want to do m.rb.velocity equals velocity, which will just apply the velocity that we calculated here into here. Cool. So, one final thing that we will want to do is we are taking in here a 3D vector, except we don't actually want to allow movement in the y direction. Now, you can solve this in two ways. You can either just make sure that no one passes a forward or right vector that has anything in the y direction, which is going up because we don't want to fly, or you can kind of cheat and come here and do right dot y equals 0. Now, if you don't add this line of code, it'll still work. Don't worry about it. But it just, you know, prevents flying into the y-axis. So, with that added here, this will seemingly make us walk in a specific direction. So we can test it out very quickly. So we said we wanted to get some input. So we can do that using some built-in Unity functions. So we can do float x equals input.getAxis horizontal. This function, along with float y equals input.getAxis vertical, will get basically either the control stick, left control stick, which you can define all these parameters in the Unity settings, but they're kind of set up by default, so most of the time you don't actually have to change them, at least for basic stuff like this, but you can all change what this is and what horizontal. You can change to like left stick, right stick, but right now the horizontal by default is set up to the left stick on a controller and the WASD and arrow keys, which is great. So we're going to do input.getAxis horizontal, input.getAxis vertical for the x and y, and then we're going to do movement controller. So I just realized I called this movement controller instead of move. Thank you, autocorrect. I'll call this move. Stop correcting me. Move. And we're going to pass in a new vector 2. Sometimes where autocorrector is useful. X, Y. And then just for the time being, we're just going to do a vector 3 dot forward. We're going to use the global forward and right of the world. and I'm missing no parentheses. I'm just making typos. And so now I'm going to come back to this line of code here, and I'm just going to comment it real quick because I just want to show you some things before we jump into it. So if you now go back to our capsule, click on it, we can see that a Unity compiled. We can add a new component, movement controller, which will add our movement controller. And as you see, it already also added a rigid body, which is awesome. And what we're going to do is, the first thing we're going to do is uncheck the use gravity bool, because otherwise what's going to happen is your character is going to actually start falling through the world, which we do not want. And we're going to click play, and we're going to look at the scene here. So if all goes well, when we click forward and backwards, our character moves, albeit very slowly, but our character moves in the XZ plane, which is awesome. Now, there's two problems here. One thing is that our character is really slow, so we would like to define some sort of speed which they can go at. So we're going to go in here and we're going to define a new public float speed. We're going to set it by default to, let's say, 5. Then here under our velocity, what we're going to do is, so this vector here gives us the direction, but this vector is not normalized, which is an important thing to note. So we're going to take this vector and then we're going to normalize it so that it has the unit length 1. And then we're going to multiply it by the speed. So now if you had not normalized this vector, its length could be anything, really. And so then the speed here doesn't actually make any physical sense because you don't know what you're multiplying it. But given that now its length is 1, you multiply it by speed, say speed is 5, now we know that we're going to be moving 5 units in the direction of this direction that we're getting. So then movement is then just defining kind of which direction we're going, how much of the forward, how much of the right we're getting, and then we'll be moving by constant speed in that direction. Now, if you want to make it go into different speeds, you can feel free. That is up to you. If you had not normalized it, what you would notice is most likely what would end up happening is the character would end up moving faster when it's going in the diagonal than when it's going forward or right. Because when it's going in diagonal, it'll have movement.y equals 1, movement.x equals 1, right? It'll be like 1, 1. It'll be going into the 1, 1 axis, right? And that'll have a length of square root of 2 as opposed to 1. And square root of 2 is larger than 1, so square root of 2 times speed will be greater. So whenever you're going diagonal, you'll be going faster. All this to say, adding the normalization lets you kind of think a bit more naturally about the speed. And if we go back and click play, we'll see that while it's compiling, now we have the speed. And if we walk around, hey, the character is moving much faster. One thing we do notice, however, hard to see with the controller, but when I start clicking, the character doesn't actually stop. And another thing is, when I'm walking right, you can see here the axes of the character. These are the axes representing the WASD that we were kind of talking about. This is the forward, this is the right, and this is the up. So one additional thing that we actually kind of want to do is, so, again, I apologize for that confusing statement I said at the beginning of the tutorial, but we actually, it's not that we want to move in the direction of the character is facing. It's more that we want the character to face in the direction they're moving, and we want to be able to decide which direction they're moving. And right now, if we move around, if we move right, you see the character's strafing. And this is most obvious if you add in an extra object, let's say a cube, that you move up like this, and then you scale. Let's say there's going to be a very rough nose. Yeah, let's say this is nose, right? You can now tell that the character is strafing, and we don't want that. So what we're going to do is we're going to go back and we're going to solve both of these issues. So the not stopping when we stop moving it, and then the rotation. So the first thing is super easy. What's happening here is that input.getAxis is actually kind of what's called lerping, linearly interpolating our values. So your keyboard is not actually an axis. It just returns 1 or 0 when you're clicking it. 1, -1, or 0. What Unity is going to do is for controllers, to avoid weird noise, it doesn't automatically return the perfect, thanks Java, doesn't automatically return the perfect value. What it's going to do is it's going to return sort of an interpolated value. So if you get a spike of noise, it doesn't jump, it'll just kind of start going towards it, and then if you go back to the normal thing, you'll just notice a tiny jitter. But in the case of here, what's going to happen is that there's no noise. You're just getting 1 and then back to 0. And when you go back to 0, it's not going to go back to 0 instantly. It's going to start going 1, 0.9, 0.8, 0.7, blah, 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 all the way down to 0. And it's going to take a bit of time. So, best way to solve this is we can just ask Unity for the raw values, because we know we're using a keyboard. Now, if you're using a controller, you might want to use getAxis, unless you're 100% sure your controller has no noise or anything like that, but or snapback. But I would recommend using getAxis for your controllers and getAxis raw for a keyboard, for example. So that'll fix kind of the skating effect. And then here, this code that I added in earlier and I accidentally did not think of, without really thinking about, this will actually fix our rotation. So all this is going to do here is that this movement call is being called once per frame. So even if we're not giving it any input, it's going to call it. So we're going to say that, okay, well, if you're actually given a direction to move in, just update the forward of this vector to be in the direction of the velocity. Just as simple as that. Now if we go back, wait until Unity compiles, and we click on our character. So now we can see here's our forward vector, here's our right vector. When you click play, we start going. Actually, there you go. So, little thing that I forgot to change is I was clicking global, which is showing me the global axis. I want to click here, so it's local. And when I click play, you can see that when I move back and right and left or diagonal, this blue vector matches it. And you can see here that it's rotating because our character is actually facing the direction. So awesome. We got it. This is perfect. Our character's moving. We got this movement down. That's perfect. Next thing we want to move on to is actually now this camera, because while this character is moving all dandy, the camera's not actually following. And not only is the camera's not following, but we actually want to get information from the camera to move the character in relation to the camera. So, moving on to the next topic that we want to implement. Camera controls. So we want to do a few things. We want to first have the camera follow the player, which thanks to Unity will be fairly simple. And we also want to implement some sort of input handling for the camera so we can rotate. Considering we're using a computer, we're going to want to use mouse controls. And we're going to, for representing kind of how the camera works, we're going to use a special fancy thing called spherical coordinates. So, one thing at a time. What we're going to do for the following is we first want to actually track the object. So I had fancy animations here which are no longer working. But you also want to look at it, at the player. So we want to both have this looking at the player. You also want to track the player's position. And those are kind of two separate steps, but we can achieve those. We can achieve both of them fairly easily by using some wonderful work that other people did before us. So, going back to our Unity scripts folder, we're going to create a new C# script, and we're going to call this one camera controller. Simple, correct? Go ahead and double click it to open it. And now we're going to think a bit about how we want this to work. So, we first want our camera to follow the player. And the easiest way to do this is to first taken the transform of the player, and let's call this a target that we're following. And let's define here a vector, public vector 3, which is going to be an offset. Here we're going to be from the player. I'm just going to capitalize it. And here in our update, what we can do is we're just going to do this dot transform dot position equals to target dot transform position plus offset. So this is going to set us at the player's position, then plus an offset. And if we define this offset properly, it'll be perfect. So what can we do? We can just get this offset here by just doing this dot transform dot position minus target dot transform dot position. And if I've added all of this correctly, if you actually replace this into the equation here, for example, you'll see that certain things will cancel out. Target.transform.position will cancel out with target.transform.position, and then we'll just end up at the kind of original position that we were at. I believe so. I know I said be proficient with linear algebra, but you know, you can make some mistakes at times. So additionally, what we want to do is we want to look at the player. And this can be done with an amazingly simple thing that Unity provides with us. For us, we can use the this dot transform dot look at target. Awesome. And with this, we should now be able to define our camera movement following the player. So we're going to look at our camera. Going to go in and add a camera controller. We're going to drag in the player into the transform. And then we're going to just position the camera so that it's kind of roughly above the player. That seems about right. And then we're going to click play. So then here, we should have gotten the position of the player. And if we move, you'll see that the camera's moving with the player, which is awesome. Dandy. We can also change the offset here, which will change it. So cool. So now we have a quote-unquote camera follow. Except the problem with this is that it's not really ideal. Representing like XYZ positions around the player is not exactly the most easiest to think of. So what we want to do is kind of think about it in a different way. Usually there's a kind of intuitive way to think about a camera around the player, and it comes to us from movies. And it's this concept that the camera is in a sphere, in a hemisphere around the player. And so the camera is kind of looking around the player and always keeping the same distance from the player. That's the key aspect. It's always the same distance, regardless of its angle from the player, and always looking at it. And one awesome way to represent this would be with angles. So we know the radius, we know the distance from the player. That's easy to represent. We want that to be 5 units away from the player, for example. And then we want it to be like, let's say, 45 degrees up from the exit plane. And then, you know, like maybe another 45 degrees around the z-axis. Which, if you look at this image here, we can represent with the Greek letters omega and theta. Theta and phi, sorry. My Greek is a bit rusty. Theta and phi. And r being our distance. This is another here wonderful picture to kind of understand it. And with this wonderful thing here, is just a different way to represent positions. It's just angles, and we can call it spherical coordinates. And spherical coordinates are awesome because they let us think about it in a different way. It's still in the same world. If you see the z, x, y axis, it's still because we're in 3D, you know, nothing changed. It's just that we're just representing stuff a bit differently. And this is kind of a similar thing to if I told you I could represent a point on a circle with x, y, z, or I could represent it with a radius and an angle. Because once you have the angle and the radius, and let's assume it's from a center position of the world or like some given position, you can easily calculate it. You know the position, you know how far it is, you have the angle, you can use um, trigonometry, sine, cosine to figure out kind of the x and y coordinates on the plane. Similarly, there is an awesome conversion from spherical coordinates to Euclidean coordinates, which we can use, which we will not derive because that requires a bit more calculus. And for our sake, this has already been figured out for us. So going back to our code, what we're going to do is we're actually just going to define here, instead of an offset, we're going to make this offset, we're going to keep it just for now so we don't get any compilation errors. We're going to add a public float radius, or you can call it distance. Set this to 4.0f just for now. Let's have a public float float phi, and I'm using the coordinates here like phi, and theta, but you can really use whichever ones you want. You can also call it like longitude, latitude, or elevation, azimuth, whichever you prefer. I'm using this so as not to confuse you with regards to the formula. And so now that we have our three descriptions, our distance, radius, which is our radius, our phi, and our theta, we can go and apply this formula here, which is the x is going to be distance times sine theta cos phi, the y is going to be r sine theta sine phi, and the z is going to be r cos theta. Now one thing to note is that we're going to come in and do it here. We're going to do float x is equal to distance times mathf dot sine, and we're going to pass in theta, then we're going to do times mathf dot cos, and we're going to pass in phi. So as I was saying, one thing to keep in mind is that actually sine and cosine functions in Unity, you take in radians. And it's a bit easier to think of angles in terms of degrees, so 0 to 360 as opposed to 0 to 2 pi. So we're just going to assume that these are in degrees and convert them to radians. So we're going to do deg 2 rad, which is just a conversion factor, and add it in to both here. Then we could copy this turn to our y, and for this one it's mathf sine of theta, mathf sine of phi, and for our z is going to be distance times mathf dot cosine of mathf deg 2 rad times theta. So this should actually give us a conversion from our spherical coordinates to the actual xyz. Again, if you're interested in how this was derived, there's a calculus proof and there is a linear algebra proof, kind of just two ways to look at it. This is just a change of coordinates, which is a very common thing that is done in calculus and linear algebra, just a way to represent things in different axes. Excuse me. But yeah, I will not go through the explanations for this video. It's a bit too complex for this. So then here, for the position, instead of offset, we can just say new vector 3 x, y, z, which now allows us to remove our offset. And if you go back into our world and cross our fingers, we'll see that we have a compilation error. Yep, because I still left this one here. Good call, Unity. We'll wait until it compiles. So we see that now we have our distance phi and theta. And let's set this to something like, I don't know, 45 and 45 should be correct. You just give me 1 second. It seems like my computer is once again checking a tiny bit. Yeah, let's just do like 45 and 45. And so if we click play, we'll see that when we increase the distance, so now we're actually at about 45 degrees from the player. If we look into global coordinates, we seem to be at about like 45 degrees up this way and 45 degrees up this way. If we increase phi theta, we should be going around. I think I might have made a mistake with the formula, so we will double check because it seems to be acting a tad bit odd. So let's just double check. So this is going to be sine cos of theta, theta, and theta. This is going to be cosine and sine of phi. And this does seem to be correct. So maybe I just interpreted it wrong. Let's just double check again. So the distance is clearly working. We're increasing it. If we do add this to 0, it actually does seem like it's working. I'm just freaked out because during the live demo it didn't work. So if we increase the theta, we'll be going around the character. If we increase the phi, seems not to be working because of some mistake in the calculation again. I feel like there's definitely something off when there should not be. So I'm going to quickly double check all this math. So this equation here is correct. You don't have to worry about it. In the code that we've uploaded online, it does work. So I'm just going to leave this here for now because I'm fairly sure this is correct. And I can't think off the top of my head what the issue can be right now. So I'm just going to move on a tiny bit. And if it keeps showing off the bug, then I'll just get some of the 100% sure code to work. So now that we have this, we actually want to take an input. So just like the other function, we want some kind of global function that's something call. But instead of move, because this is being updated once per frame, we want something to modify this distance phi and theta. So what we're going to do is we're going to add a public void rotate by. Just going to take in a float theta and a float phi. And just going to do this dot phi plus equals phi and this dot theta plus equals theta. So we're just going to modify it by some amount. And then we're going to do a public void zoom by float amount. We're going to do distance plus equals amount. So we can zoom in by some extra amount. And then finally, we move on to the input. Because for the input, we're going to want to do something a bit special. It's not going to be as easy as what we did for the player, but it's going to be fairly easy. So since we're using a mouse, what we're going to want to do is we're going to want to do some drag input. We're going to want it to sort of replicate the behavior in Unity where you can drag and rotate like this. Except in this case, when you rotate in Unity, sorry, it's compiling, you're kind of rotating around your own axis. Here what we want to do is when we kind of drag, we want it to go around the player. But in terms of the actual controls, you get it that we want to like be able to drag like this. So we want to detect when a mouse is being clicked. That's the first stop. We want to keep calculating the difference in position while it's being clicked. And then we want to detect when the mouse is released. And then if we get this change in position while it's being clicked and keep using it, we can modify, we can turn that into a direction, into our theta and phi, and then we can just move by that amount. So, I kind of jumped ahead of myself, but going back to our code, we can actually come in here and use some really cool functions that Unity has. So, we can get the current mouse position. So for all of this, we're going to need a few extra variables. So I'm gonna make a new vector 2, which I'm gonna call m delta. So it's gonna be the change in position. I'm gonna make another vector 2, which I'm gonna call current mouse position. And then I'm gonna make a final vector 2, which is gonna be last mouse position. So what these are going to let me do is track the last mouse position, track the current mouse position, and then calculate the difference between them. Now, do I really need this delta here? Oh, not really. I can, I can just like pass it in directly, but it's just nice to have, so it's a bit clearer. So now going into our code, we're going to go into our update, and we're going to do m.current mouse position. We want to get the current mouse position. Very easy. You can do m.get mouse. Sorry, not get mouse, just mouse position, because it's a parameter that gets updated by Unity. So now we have the current mouse position. Perfect. Next step is we want to update the last mouse position after some block of code to be the current mouse position. So here we're going to have a block of code that does stuff. We're going to think a bit about what it does. So we said we want to detect when the mouse is being dragged, when it's being clicked, and only calculate the delta then. So what we can do is we can use Unity if input.get mouse button down 1. So what this is going to do is it's going to tell you, actually if you hover over it, it'll tell you returns true during the frame the user pressed the given mouse button. So this is going to return true. It's going to return true when the player presses down on the mouse. So in here, we can update our delta because we know that the button is being pressed. Okay, this is equal to m.current mouse position minus m.last mouse position, right? Easy. Except that these mouse positions here are actually relative to your screen density, your resolution. So it's going to return you a big number, and it's going to change depending on resolution. And we don't want to actually move faster if you have a bigger screen. So what we're going to do is we're actually going to sort of normalize this. And so we're going to do minus.mdelta.x divided by screen.current resolution.width. I'm going to do m.delta.y divided equals by screen.current resolution.height. So this is going to return a number between 0 and 1, telling us how much we've moved, what percentage of the screen we've moved in. Okay? And then we're going to say that if there is no mouse button down, we're just going to zero out the delta, because otherwise it wouldn't do it on its own. It would be set to it and it will keep updating. And so this is actually most of the code we need. Now when we have the button down, we can calculate what the change in position is. And we're storing this change in position every frame. And we can actually do this a different way. If you'd like, we can actually calculate the delta every frame regardless, and then only if the mouse button is down we can apply it. But different ways to do it. I try and avoid doing the calculation if I don't have to, but actually at the end of the day, it depends on which one takes more time, but there's no need to optimize at this point. We can just call rotate by, and then we can pass in dot delta dot y dot delta dot x, which will rotate us by this amount. Now, as we're running a tad bit short on time, I'm going to skip teaching you the hard way some of the mistakes. And I'm going to tell you right now that similar to the speed for the movement, we also want our rotation speed. So what we're going to do is we're going to add a public float rotation speed, and then we're just going to take this and multiply it by actually take this here and multiply it in our phi and theta. So there's different ways to do it. You could multiply it by this input here, but just like the velocity, we kind of want this to be a property of the controller, the camera. So we're going to add it into this rotate by, and it'll allow us to move when you give us between 0 and 1. We'll move by that percentage, by like percentage of the screen will move by a certain amount of unit of degrees per, so if you move by 1% of the screen, we'll move by 1% of this speed for that frame, which is cool. So now, fingers crossed for this to work. Final thing we're going to do is I'm actually just going to add m current mouse pause equals m last mouse position at the beginning, just so they're set to the same thing, because in theory they should be both set to 0, but something could happen. I like to make sure. I think this was like a very late night thing that I added just out of craziness. You probably don't need it, but So going back into Unity, I can compile. If we cross our fingers and press and add in here a rotation speed of like say 30 degrees and press play, well, we see that it's definitely moving. So something seems to be happening if you look at this angle, but it seems to only be happening the frame we press down our button. That's actually because I made a mistake and I used the wrong function. So get mouse button down actually only returns true the moment you press the mouse, and not the entire duration that you have the mouse down, which is wrong, because what happens is that you're only moving the camera that one frame that you started pressing the button, but not during the frames where you're still holding it. So changing it to mouse button is going to return whether the given mouse button is held down regardless of the frames, which is actually what we want to do. So going back here, and this is the kind of these are kind of errors you find easily once you've made them a million times. Going back here, if we rotate, we can see that we can rotate around the player. So now actually we're getting sort of this behavior. Final thing we want to add is we actually want to zoom in and out, and we can get this fairly easily by coming here and adding so we're just going to move this after this code. Going to do a zoom by, and we can actually very easily get the scroll wheel by doing input.getAxis, this function that you know and love now, and just write mouse scroll wheel. The reason why I multiplied by -1 is because the way the scroll wheel is calculated is that if you scroll forwards, it's positive, but we want it to be negative so that we decrease the radius. So going back, if we play, mouse scroll wheel is not, it tells us that mouse scroll wheel is not set up. It usually is by default, but that's because I put in a typo. It's a capital W. So let's go back and play. So if we scroll in and out, you can see that we can zoom. So cool. So now we can move around, and we can zoom in and out. Awesome. And now we come to the final issue. So we have this movement controller, which this code here doesn't really depend on any input. You can pass it any code. You could technically even use this for an AI. But the input is here. Same thing with the camera controller. This doesn't actually require the input to be done here. It just needs to be told from someone how to rotate. Some system could tell the camera, hey, rotate to look at a treasure chest. And so it kind of doesn't make sense to have this input here, because then it prevents us from having this kind of logic where something else tells it to do stuff and it's not tied to the player, because right now this is only tied to the player. We can only have a camera that works on the player. So we're going to add kind of a script to unify our input. and not only unify our input, but it's going to allow us to pass in that extra information about the mouse, about the camera that we need for our character to move in the direction that the camera is facing. So going back to Unity, let's add our last final script, which we're going to call character controller. And so opening up our character controller, it's going to be fairly simple. So character controller, I actually realized that in the repo I called it a player controller, so I'm just going to change it to player controller for the sake of continuity, so as not to confuse you. So I'm going to call it player controller. And here, very simple. We want to take in public. There's a few ways to do this. Now, in the repo, I got the components of the movement control and the camera controller. You can also make these public and just drag them in and out. So I'm going to make these private to kind of show you how you can retrieve things. I'm going to make a private movement controller, which is the thing that we want, and call mmover, a private camera controller, and then I'll call it mcam. And right here we're going to say that this is going to be on our player, so we're going to require that it has our movement controller. So you don't have to put this on the player, you could put it on something else and then retrieve the player and then look for a movement controller on them. But we're going to assume that this is on the player, that whatever this is on requires a movement controller because it's going to be the player. Again, this kind of decisions end up being your own to make. This was simple enough for right now. And so then we're going to go in here and I'm going to get mmover equals this dot get component movement controller. And then we're also going to do mcam equals camera.main, which tells Unity to retrieve the main camera in the scene. Dot get component camera controller. Now there's no way here for us to ensure that the camera has a camera controller, which you'll notice. This is the one issue with this one. So if you go on the camera and there's no camera controller, you know there's going to be a problem. But again, this was kind of just to show you how you can retrieve things from the main camera, how you can retrieve things through get component, and not specifically just like dragging in and out of the inspector. And then here in our update, all we're going to do is we're actually just going to go into our camera controller and take all of this good stuff, paste it here. And so then we're also going to go and take this, paste it here. We're just copy pasting. Take all of this information. I'm going to add it here under camera input variables. And then here under these methods, we just need to call it under mcam. Cool. So now we have our camera in our character controller. We're going to go do the same thing for our player. We're going to go into the movement controller, and we're just going to take all of this here and drag it out and put it here. Perfect. So now we have extracted all of the code into this one class, and now we can add a movement controller to an AI if we want and have something else called the move function. Add this camera and then have some sort of maybe director make you look, or like cutscene make you look at something else. It's a good way to do things, so that you don't have needlessly tying dependencies together. And now the last thing that we want to do, which shows you why this would be also useful, is we will no longer use the forward vectors of the world. We're going to actually use the forward vectors of the camera. So here we have the camera, and we can get its forward and right vectors, which will allow us to move in the direction of the camera when we're playing. And so I know I went through this a bit quickly, mostly because there's a lot of copy pasting code, and it's just tying in a lot of the stuff that we already learned into one class. But now if you go back to the capsule and add player controller, usually there's nothing to connect because it kind of will find everything on its own. But if we play, we're going to cross our fingers that this is going to work. Alright, so getting issue saying that the main camera does not have a camera controller. Why is that? The main camera does have a camera controller, but it's not tagged as the main camera. So we can find the main camera. So now we tagged it as the main camera, so it should be the main camera. So now you actually have our controls. And the interesting thing is going to be that if we look here, it's a bit hard to look in the game because there's no point of reference. You'll see that the character is always moving relative to the camera. So we still have this bit of an odd bug with the movement, unfortunately, but it will be corrected in the source code that we post. I'm really sorry about that. But as you see, as we move the camera, as I move the camera angle, when I press forward, the character will move relative to the camera. So if I do this, the character is always moving relative to the camera. If I click on the player, make it the local, you can see that it's updating its position relative to the camera. So that's awesome. And that kind of covers the main things that we kind of really wanted to look at for this tutorial. Now, we didn't have time to add in a character, but linked in the GitHub repo will be two packs of assets, the nature pack and the Kenny character pack, which we will just use to drop in and add a little character instead of this capsule and a little world to walk around in. And that'll allow you to have a bit nicer, that'll allow you to have the picture that we showed a bit earlier in the slides over all the way at the beginning. Oh, we've gone far. Have this little character here with the world walking around. None of these, but at least like a little floor. We'll let you kind of figure that out. It's not too complicated. If you're familiar with Unity, it should be as simple as dropping in your new assets here and then replacing the capsule with the new asset. As I said, all the code will be on GitHub. It will be a corrected version, taking into account the rotation. As soon as I figure it out, I will post it, and hopefully we might post a corrected video tutorial for this. But yeah, if you have any questions about this, feel free to ask us on Discord for all of our members. Also feel free, you can show up to the club room at any moment if you need questions whenever we're there and we have office hours. Again, my apologies for any hiccups during this tutorial. First time recording it, but I hope you enjoyed and hope you learned from it. Thank you, everyone.